Okay, so let's find the double integral of 5e to the x squared dx dy with these bounds. Okay, so let's go ahead and start. Where do we start? I guess with U substitution. So let's say that u is equal to x squared. And du is then going to be equal to 2x dx. Alright, so what are we substituting in for? Well, of course we're going to substitute u in for x squared up here. That's what's defined up here. But for dx, we're going to have to solve for dx to plug something in. So dx is equal to du over 2x. Now that we have this identity, right, we're going to go ahead and plug that into our first integral here. So keep in mind that the way that we're solving this is we're doing the first integral first, and then we're doing the outside integral second. So right now we're still working on the first integral, right? Okay. Now let's plug stuff in. Important step to remember is that we need to convert our bounds. So our bounds go as this equation goes. So we plug our bounds in for x in this equation, and then u is what we plug back in for our bounds. So our lower bound is 3y. So 3y, all of that squared is 9y squared, right? And then 12 in for x, so 12 squared is going to be 144. All right, so we have 5 times e to the u, right, because x squared is equal to u. Then we have for dx, du over 2x. Now, there's an issue here, and that is that we're still left over with an x. We can't figure this out. It doesn't work, right? Because x, what is x? X isn't a constant. X is a different variable. At this point, we've done all this work to substitute u for x, but we're still left over with an x. So none of this works, right? So let's go back to the beginning. One nice thing about double integrals, or any series of multiple integrals, is that you can switch around the order of integration. But what that also does is it ends up, changing your bounds as well. Or changing the way that you write your bounds, right? Your bounds are still the same in theory, but it changes around the way that we write them. So to understand that, what we're going to start by doing is graphing our bounds. This is a good way to start any problem like this, is by graphing your bounds. X-axis, y-axis. So for x falls between 3y and 12. Now, what are these right here, the lower and upper bounds? They're actually functions of x. There's an invisible x equals in both of these, right? And if we look at our y bounds, there's also an invisible y equals in here as well. So let's go ahead and graph these. So we have the upper bound is the easier one to do, so let's do that one first. X equals 12, right? Okay, it's horribly not straight line, but x equals 12. And then x equals 3y. So that has a slope of, I don't know, something like this. Yeah. Yeah, and it keeps on going in that direction too. No, we were doing dashed lines, weren't we? Okay. Okay, and then we have for our y bounds, we go from y equals 0, which is just the x-axis, right? So this is just y equals 0. And then we have y equals 4, right? Which actually you'll find if you plug it in intersects right there. So, which region is enclosed by all of these bounds? So you might be tempted to say this region right here, but that would actually be wrong because we don't actually have a bound right here. There is no bound at x equals 0. That isn't an equation. So it's actually this right here. It's enclosed by all of our bounds on all sides. It's enclosed by y equals 0, by this equation, which was x equals 3y, and by x equals 12, and it's, well, yeah, that's everything, right? Oh, and also by y equals 4, of course. Okay, so now let's flip our order of integration and write our integral accordingly. So we have our two integrals. Let's skip writing our bounds for now. Our function remains the same, right? dy dx. Okay, well, we flipped our order of integration. We're going to do dy first and then dx. Now, an important thing to remember, we're going to work from the outside in when we're defining our bounds. And the reason that we're doing this is because on the outside, our bounds cannot, our outside bounds cannot be a function of any of our inside variables, right? So our x bounds cannot be a function of our y bounds. Our inside bounds can be a function of any variable that's outside of it. So our dy bounds can be a function of x, but not the other way around. So what does that mean? That means that for x, we're just going to do bounds where x equals just some number, right? Your outer bounds will always just be some number. They will never be a function of anything. So let's go and look at what that looks like. Well, x values for this region right here, for this region R, x always falls between, what is it always greater than? It's always greater than 0. It's always less than 12. Cool. I mean, that's true. It's not the same bounds that we were given over here, but we expected that, right? And then our y bounds, remember now we can be a function of x, right? So for any value of x that we've just picked that's along here, right? For any of those values, it goes from y equals 0 to, well, it goes up and it hits this function, right? So what is this function? Well, it goes from 0 to whatever that function is. Well, we know what that function is. It's x equals 3y, but we need to solve it for y, not x, because in this case we're figuring out what y is less than, not what x is less than. So solve for y, and we get x over 3. That's simple. Okay, so our lower bound here is 0, and our upper bound is x over 3. Great, now we can take this guy, and we can solve it. Okay, so we reversed our order of integration to mix things up a little bit so that hopefully we don't end up running into the same U substitution dead end that we did before, where we had an x in the equation still after doing U substitution. We don't want that, so let's see what happens this time. So again, we're going to be working just with this first part here, right? This first integral. So integral, well, let's start by looking at this. So we're integrating with respect to y. So don't start doing gymnastics with x, we don't worry about that because right now x is a constant. We're integrating with respect to y, so x is a constant. So all of this is just some number. What happens when we integrate just some number? All that we do is we tack on a y to the end of it and we call it good, right? So don't overcomplicate this. This is 3ex squared times y. And that's it, right? And of course we go from our upper and lower bounds. Equals, okay, let's plug in our upper bound. We get 5ex squared times x over 3 minus whatever our lower bounds plugged in would be, which is 5ex squared, 5e to the x squared multiplied by 0. So this all becomes 0. So this is what we're left with. All right, so we have 5ex squared times x over 3. Okay, well, now let's move on to our second integral. Our second integral is going to be 12, 0 for our bounds, e to the x squared times x over 3 dx. Okay, now let's try U substitution again like we did last time. But I have a good feeling it's going to work out this time. So U equals x squared, just like we did before, right? We're picking that because that's the part that's kind of the most complicated, that I look at it and I'm like, I'm not really sure how I'm going to do that, which is this part right here. So x squared is what's going to be, well, we know how to do e to the u, right? But we don't know how to do e to the x squared. So we're going to substitute that x squared with u. So u equals x squared. Du is the other thing that we need to figure out. That's going to be 2x dx, right? We just take the integral of whatever u is equal to, sorry, the derivative of whatever u is equal to, and we put it down here, and we tack on a dx at the end. Okay, for substitution purposes, we need to figure out what dx is equal to. So dx is equal to du over 2x. So far, so like everything is the same as it was before. Let's plug everything in and see how it works out. So remember that our bounds need to be plugged into our equation for u, right? So 0 squared is 0. 12 squared is 144. Great. Now 5 times e to the x squared, which turns into u, times x over 3 times whatever dx is equal to, which is du over 2x. Aha, okay, now our x's cancel out. Sorry, this is not dx, this is 2x. Anyway, our x's cancel out, and we're left with integral from, 144 to 0 of 5e to the u times 1 over 6 du, which of course all this just goes away, and this is 5 over 6. All right. Okay. Now let's solve for this. Now, since 5 over 6 is just a constant, that stays the same. Then we have ln of u from 144 to 0. And this is all equal to, let's plug in this, so we get 5 over 6 times ln of 144 minus 5 over 6 of ln 0. Now, what is ln 0? ln 0 is actually just 1, if I remember correctly. So all of this goes to 5 over 6 times ln 144 minus 1. Alright, I actually made a complete fool of myself here, so this is actually not that, because the derivative of e to the u is not ln u. It is going to be just e to the u, or the integral rather. Both the integral and the derivative, they're exactly the same. So we have 144, 0, 5 over 6, e to the u. Well, actually, let's get rid of that because we're taking the integral now. Respect to 144 to 0. Okay, then we plug in, and we get 5 over 6 times e to the 144 minus 5 over 6 times e to the 0, which is then just going to simplify it to 5 over 6 times e to the 144 minus 1. Okay. Now that I am fairly certain is the correct answer. Okay, if this helped in any way, please let me know. Sorry for the blunder, but after checking, I am certain that this is the right answer, and please leave a like and a comment if this helped you out any. Thank you.